Welcome back, AP Statistics. This is the second part of Chapter 9, where we are manipulating data a little bit in a way that does not corrupt the data. We're applying functions to each data value and seeing if we can make the data more symmetrical or straighten out a scatter plot or something like that. So we're actually going to do something unorthodox here. I'm going to review the part of the last video that talks about how to transform data. I want this fresh in our heads. I'm not just going to say go back and watch the last video. I want this to be fresh in our heads for this video. So here we go. We're going to use the ladder of powers here. And the ladder of powers, the first one we talked about, the first data transformation, we call 2. All right, that refers to squaring. It's the mildest of adjustments. Data that are skewed to the left can benefit from this. We can take this left skew graph and make it nice and symmetrical that way. So left skew, we would want to square the y values. And these are all adjustments to the y values of points. We're not adjusting the x values yet. Emphasis on yet. If data are already almost linear, or they can assume positive or negative values, or don't have boundaries, there's no minimum or maximum possible value. That's rare, but it does happen. The data don't usually benefit from re-expression. It's best to just make like the Beatles and let it be. 1/2 refers to applying a square root to the y values. It's often helpful with counts of some kind. Next up is 0, and that stands for the logarithm, interestingly enough. Logs are useful for transforming data when the y values cannot be 0 or negative, and is usually helpful for skewed data that is left or right. Logs have the awesome property of making big numbers small and really big numbers almost as small. Now to the really powerful transformations. We have -1/2, which is the negative reciprocal of the square root, or we also have -1, the negative reciprocal, and that is the most potent of adjustments. These are sometimes helpful for units that are ratios, okay? If we have a ratio and the data are curved, like we have over here, flipping that ratio can straighten things out. And remember, we want the negative reciprocal square root and the negative reciprocal so that our data are going the same way. If our data are down and to the left, I want these data to be down and to the left too. We did a couple of examples last time. You can feel free to go back to the last video here if you would like to see these examples on what is the best transformation to apply. All right? So we're going to skip right ahead. Now we're going to experiment with the ladder of powers using our calculator. Here's a scatter plot that details the length of a fishing line on the spool and the strength. So if we were to fit a regression model to this, we'd be able to predict the length of a fishing line given the strength, the test strength, we would say in pounds, okay? So the length of a fishing line and the strength of that fishing line are related. Strong fishing lines are not of great length. The stronger we go, the further the length of the line. But we have this kind of 1/x kind of fellow right here, and we'd like to straighten that out. So let's use the ladder of powers. I'm actually going to forego the squared idea, and I'm just going to go right to the square root. All right, so we're going to go to the square root of length right here. And we've made a little bit of progress, all right? The curvedness is not as exaggerated, but we can certainly do better than that. Now I'm going to try a log, Okay, let's try a log. So we did log length, and this is starting to become a bit more linear. Our data transformation is more effective, but still it is markedly curved. So now I'm going to look at the more potent transformations, and we have, let's just go right to the most extreme, -1 divided by the length that is the reciprocal, negative reciprocal of our data values. And wouldn't you know it, our data are actually starting to curve the other way. This is good. This is almost linear, but it's interesting. The data are curving the other way if you look closely. This might be our best one with the possible exception of up here. Once we get to this point, it's pretty much a line. So it's a toss-up whether you want to use the reciprocal, the negative reciprocal, or the negative reciprocal square root. Both are quite good. Yeah, that's the power of transforming data. Okay, so how do we use this? Well, I'm now going to be referring to the negative reciprocal square root, partially because it is algebraically the most interesting and gives you good practice. Okay, so the linear regression model for the negative reciprocal square root re-expression is this guy right here. Now notice we're still predicting lengths, but our predicted length is square rooted, reciprocaled, if that's a word, and the opposite, okay? So we're still predicting lengths, but in a messier way. But we can fit a regression line to this because these data are much more linear than what we started with, okay? So now we're going to use this model to predict the length of a line with a strength of 35 pounds. And we're going to need to use some algebra. The way we do this is we say, okay, my strength is right here. I'm going to put 35 pounds, substitute that for strength. And if I do that and I solve for this square root fellow right here, I would substitute 35 for strength. I would multiply square root of length on both sides and divide both sides by this whole right-hand side. So the whole right-hand side I'm putting in the denominator over here, and the denominator of my left-hand side is on the right. Okay, so I did a little switcheroo between the denominator of the left-hand side and all of my right-hand side. And I substituted 35 in for strength. Now what I would do is square both sides, and then I have a predicted length. So I can put this into my calculator. Please be sure to use parentheses in your denominator. Make sure that you group the whole denominator together, or else your answer will be very, very wrong. And we get an approximate length of 769 yards. Okay, so that is the length of the fishing line that we predict given a strength of 35 pounds. So now we're going to take a really hands-on approach to this skill of altering our data values without corrupting them, specifically the Y values. A biologist is studying a type of bacteria. Let X be the number of bacteria in the petri dish, in thousands, at the beginning of the day, and let Y be the number of bacteria by the end of the day, also in thousands. So we're going to first make a scatter plot of the data on the calculator, and you'll see that the data do not follow a linear pattern whatsoever. Then we're going to proceed down the ladder of powers until we find a re-expression that fits a linear pattern, and we're just going to re-express Y at this point. Check the residuals for patterns to make sure. And then step 3, we're going to do a computation. But first, let's do steps 1 and 2 on the calculator. So we're back at the calculator, and here are the data entered in to list 1 and list 2. I'm going to go to second and then up to stat plot. We're going to make sure that our first plot is on, and it is indeed on. I'm going to hit enter. And then we're going to go down to the type, and we see that the type is in fact a scatter plot. From here, I'm going to go to zoom, and I'm going to go to zoom number 9, which is zoom stat, and that is definitely curved. So what shall we do? Well, we're going to start this one differently than last time. I want to show you how to manipulate the data without corrupting it, how to perform a data re-expression just using the calculator. You don't have to do all this by hand. That would be awful. So let's go to our data again. So we go to our data, and we're going to go to Edit, and I'm going to go to List 3. I'm going to hover over List 3. So I'm highlighting List 3 right now, and I'm going to define List 3 to be something. I'm going to say, let's take second List 2, which is right above 2, second List 2, and I'm going to square it. So I've just made a rule for List 3. If I so much as hit Enter, behold, I have squared all of the values in List 2. For example, 8.5 squared is 72.25. 9 squared is 81. 10 squared is 100. So now I'm not comparing List 1 to List 2 anymore. I'm comparing List 1 to List 3. That would be my data re-expression. So now I'm going to take my re-expressed data and I'm going to put it into a scatter plot. So I'm going to hit second stat plot. I'm going to go to that plot. And I'm going to change List 2 into List 3. So I'm going to hit second. I'm going to hit 3. So that gives me List 3. Now, for whatever reason, if you try to zoom stat, it gives you something unusual on this calculator. So I'm going to go to the top, and I'm going to hit zoom. And we're going to do zoom number 9 for zoom stat. Okay. So that actually got worse. So we're going to have to go back to the drawing board. And I'm going to show you how to do each of the other transformations, all right? So we're going to do the 1/2, the 0, the -1/2, and the -1. So let's go to stat again, go to stat, go to edit, and we are going to manipulate, legally of course, our data again, all right? So we're going to do another data re-expression. I am now going to define List 3 to be not the square, but the second square root of all of List 2. There it is. And now I'm going to hit Enter, and I got a bunch of square roots. So that's how I would square root my data. Now I'm going to show you how to do the log, okay? So I'm going to say, here's log base 10. That's natural log. That'll work as well, but we use common log conventionally. So we're going to use common log of List 2, and I can hit Enter on that. And then I got a bunch of logged values. That's awesome. Now the next in line is the opposite reciprocal square root. This is the most complicated by a little bit. So I'm going to go up to List 3 again, and I'm going to say -1 divided by the square root of List 2. So this is the opposite reciprocal square root of List 2. So I hit Enter. I got another set of values right there. And finally, my most potent transformation would be the opposite reciprocal of second List 2. So that's just opposite reciprocal. And so you've seen all the ways now that I can transform my y values of my data using the ladder of powers. I'm going to show all of the transformations at once, and then we're going to pick which one is best on the next slide. So here is my original scatter plot, and obviously it's not that great. We square the y values and it actually gets worse. Then we apply a square root and okay, we're moving in the right direction. Then we apply a logarithm and that's not bad. That is certainly linear. Then we try the opposite reciprocal square root and that's quite good. But the winner of this selection of data transformations is the most potent one of all. Usually we don't need to get to this point, but this is the coup de grace of data transformations, and we have thunderous applause because we have taken these curved data and made them rather linear in form. Look at us go. Okay, it's time to check the residuals. I'm going to go to Stat, Tests, and linreg t-test because in order to check the residuals, I need to compute the regression lines equation, right? So I'm going to do that. And I notice I have list 1 for my X list, and for my Y list I have list 2. I actually don't want that. List 2 is my original Y values. I want my transformed Y values, which are in list 3. I'm going to go all the way down to the bottom, skip over all this stuff, and we compute the regression line. Now I'm going to go to second stat plot. Now I can compute the residuals. Okay? So I go to this plot right here, and I make sure it's a scatter plot. I have my X list is list 1, and my Y list is residuals. I do not have that option unless I've computed the regression line. You need a regression line to have residuals in the first place. So I'm going to go to second list just to show you how you get the residuals. So second list is above stat. You get residuals that way. Option 7 will not appear unless you've computed the regression line. Okay, so now I'm going to go to zoom. I'm going to go to zoom number 9, and that is a nice residuals plot. We have some points above, some points below, but it's kind of chaotic, which is exactly what we're looking for. So we're back to the original question, and we're ready to do part 3. We've already made a scatter plot, noticed the nonlinear pattern of the data, proceeded down the ladder of powers until a re-expression fits a linear pattern. We had to go all the way down the ladder of powers, but it was worth it. We needed to check the residuals to make sure our residuals checked out fine and dandy. Now, step 3. Compute the equation of the regression line. We've done that, but I'll state it explicitly using the format we like to use in AP Stat for this data and approximate how many thousands of bacteria would be in the petri dish by the end of the day if 9,500 bacteria were put in the dish at the start of the day. So here's our regression information. I had to recompute the regression line in order to scroll down to find B, but A, our y-intercept in this form, and B, the coefficient of x in this form, are both given there. And so we will use this information right here in the context of this formula to take an x value and find a predicted y value. And we'll need to remember that the answer we're going to get for y is the opposite reciprocal of our actual answer. So here's our regression line rounded to 4 places. Notice that the predicted bacteria at the end of the day is in the context of an opposite reciprocal. So if we were to substitute this 9,500 into bacteria at the start of day, and note the bacteria at the start of the day is in thousands. So I'm actually going to substitute not a 9,500, but a 9.5, because that's the number of thousands of bacteria I have at the start of the day. So substituting 9.5, this whole left-hand side would evaluate to this number right here, rounded to 4 places. So this negative 0.0571 number, that's this whole left-hand side. That's how that would evaluate. Then if I were to divide my evaluated left side on both sides and multiply both sides by the predicted bacteria at the end of the day, that would allow me to find the predicted bacteria at the end of the day. So that solution would be 17.5224 thousand bacteria. So approximately 17,522 and change bacteria would be what we would predict by the end of the day.